This is Chemistry 302, lecture number 7 on chemical equilibrium. In this lecture, we do a better job of explaining K in the context of the mass action quotient Q. We'll tidy up some details about the relationship between Q and K. We'll investigate a little bit more what exactly is involved in creating the equilibrium constant K, what the rules are for how we set one up. And then, most importantly, we'll spend some time looking at Le Chatelier's principle. Le Chatelier's principle provides us with a qualitative idea about what the relationship is between Q and K in the context of how you manage stress in a system. And we'll develop a simple strategy for how to predict whether a reaction will shift to the left or to the right in response to a stress. And finally, to wrap up Lecture 7, we'll take a look at the Van't Hoff expression, which is a way for us to provide a quantitative explanation for the temperature dependence of the equilibrium constant K. We'll actually be able to stick in values for temperature as a function of K to calculate new values of K at new temperatures. To begin, we'll take a look at this reaction time coordinate, which gives us a good sense of what Q and K are. This is something of a review. We'll see this over and over again as I help you to appreciate what the difference is between Q and K. So here we have, as a function of time, a change in concentration. So this can be, for example, a reaction in which A is my starting material and it's disappearing over time, and B is my product and it's appearing over time. So this overall reaction would be written this way, in which A goes to form B or B goes to form A over the course of the reaction. In this particular case, it's all A to start, going away, B is being formed. At any point along this time coordinate here, I can ratio A and B, and K in particular is equal to the stuff on the right over the stuff on the left. And it's pretty easy to see that initially Q, which is that ratio, that quotient, is 0 because I have no B and a lot of A. And then as I move to the right, you see that I have ever-increasing amounts of Q being formed here. So after 2 minutes, it's equal to 1 because I have 2B for every 2A. And then at time 4 minutes right here, you'll see that I get to the point where B is equal to 3 and A is equal to 1. And it stays that way at 4, 5, 6, and so on after that. I have this quotient in which Q is equal to 3 is equal to K. It's really important to understand this equilibrium expression, the K that it can generate, and the fact that Q is approaching that K value. And you'll know that you're at K when the slope does not change for the concentration of any of the species. You have a dynamic equilibrium back and forth between the species, but their overall concentrations do not change.